It's the last activity. This one's, if I remember this correctly, this one's pretty different. This doesn't involve GeoGebra, but it does kind of require you to understand how a unit circle works. So if you guys have seen the unit circle already, that's going to help out. If not, like I'll explain it a little bit. So we're going to use this in real world scenarios, determine measurements of 3D shapes. I don't remember that part of it, and define characteristics of vectors. All right, so in the following activity, we're going to use real world examples to use 3D geometry. So we're going to give real world examples of this. I might just gloss over this, not really write them in, because this should be stuff you guys know. So, like, give me a second, because it's very weird that we're doing shapes right now. I did pick the right one, right? Yep, Unit 5, Trigonometry and Geometric Modeling. All right. So try to think of like your own real world examples. You have to make two. So a rectangular prism, it's really weird that we're doing this. Rectangular prism is, think of it kind of like a cube or like a book. Well, I guess that could be one of your real world examples. It's just a rectangle in 3D basically. And a triangular prism. So the idea of a prism is that it has a base, a bottom part, and then it has a height and a it has height and depth as well. So let me kind of explain what I mean by that. This is really weird. It's like we're gonna do trig, and then all of a sudden we're gonna talk about shapes. So a triangular prism would be like the bottom is a triangle, and then it goes up. So that would be example of a triangular prism. I probably should have made the black thing a dotted line, but you guys kind of get the idea. I can't draw. I'm sorry. Hopefully, you guys understand what I mean when I draw that. Um, the other thing, cylinder, I'm sure you guys have seen it. A cylinder is basically also a type of prism. It's just looks a little different. And I don't know why, like, it's like this is a prism, this is a prism. We're gonna call this because the base is a circle, we're gonna call it a cylinder. And a cone, I don't think I need to draw the cone, but you guys probably know what a cone looks like. Pyramid. Pyramids can be a little different, but the main idea of a pyramid, it's a it's basically a cone with a different base. So the base is different, but the idea is still kind of the same. It's still this ends up with a thing there. And the spear is just like a ball or something. So just that's all you're doing is coming up with two real world examples. Two or three? Three real world examples of those shapes. That was really random. Why are we doing this? This is random. Where's the trig in this? Do we do trig? Okay, we do get to trig eventually. I feel like this stuff's kind of out there, so it's a good thing I'm making this video for you guys then. So, what we're going to do here is we want to kind of think of a slant height. I think what this is doing is this is introducing you guys to semester two, because semester two, you guys will be doing a lot more shapes. So, imagine that's what this is doing. For some reason, I thought this was a Unit 6 activity. Find the slant height of the cone. So let's think about that. A slant height would be this AB. So what it's basically telling us to do is we have to think of this as a triangle. Instead of thinking of it in 3 dimensions, let's think of it in 2 dimensions. So this is where this benefits us. Now the problem is they don't tell us what this is. but they do tell us what the diameter is. So this whole thing is 4, so half of it should be 2. So we do kind of know what this is. This is a 2. And then here, this is a 6. And this is going to be what we're solving for. This is our x. So this allows us to find the slant height. So when we're solving this, we're going to say we use the Pythagorean theorem to solve the slant height. And then you just solve for it. If you want, and what you should do is like 2 is the a since it is half the diameter, and they gave us that. They gave us height. I guess you should be saying they gave me the height. I keep saying us because I'm teaching you guys. So here, this is where you're going to do your Pythagorean theorem. So you're going to say AC squared equals 2 squared plus 6 squared. And you're just going to solve it like that. I don't think I need to solve this. I'm pretty sure you guys understand how to solve this by now. Just make sure that you take the square root to solve for it. I'm okay with you guys leaving it as a square root of something. I don't expect you guys to reduce it because we haven't gone over that. Find the measurement of the angle formed between the slant height, between the base and the slant height. So they're asking us to find this angle right here. So here's some more trig. So I'm going to call this theta for now. So if I'm finding this angle, like I could technically solve for use the x, but I'm mainly thinking I'm going to use my opposite. And this right here would be my adjacent. So I'm thinking SOHCAHTOA, right? So SOHCAHTOA. So if I'm thinking SOHCAHTOA, I'm thinking what I'm going to do is I'm going to use my TOA, my tangent. So whenever you're writing these down, you want to write it down as tangent of theta equals opposite over hypotenuse. Remember when you do it to show your work. So type it in here. Ah, damn it. Sorry. So you're going to type that stuff in here. So you're going to go tangent of theta, blah, 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 blah. And you're going to plug in your work. So you're going to do tangent of theta, which we don't know, equals our opposite. If I scroll up, I said my opposite was 6 and my adjacent was 2. So I'm going to say opposite over adjacent. I don't know why I said opposite over hypotenuse. I don't know why I was thinking sine. Opposite 6 over 2. So I'm looking at tangent theta of 3. The only way to get rid of a tangent is to do tangent inverse. So you're going to do tangent inverse of 3, and that's going to give us our theta. So try to do it by a few decimal places. I never like how many decimal places like Edmentum uses. I feel they always give you way too little. And that'll be how you solve for that angle. So make sure you're showing your work, otherwise you do get points taken off. And then the last one, imagine two segments represent the slant height. Segments are on opposite sides, meet the apex. So they're asking us to solve for, oh my gosh, why do they word it so stupid? Imagine two line segments where each segment represents the slant height. Okay, I get it. Line segments are opposite sides, okay, and meet at the apex. Why do we have to imagine that? That's already a thing. Find the measurement of the angle formed between the lines. Okay, so all of that weird talk just to say that they want you to figure out this angle. So what you're gonna have to do for this one is you're after you figure out what theta is, you're gonna do 2 times whatever that angle is plus I'm gonna call it beta because I don't know. Like you guys can use your own variables. You can call it 2x plus y equals 180 for all I care. Like you don't have to use the Greek symbols. You can use any variable you want. The reason why we're doing 2 is because this is theta, this is theta, so we have two angles. So we're going to do 2 times that angle, and we need to figure out this y right here. So if I want to figure out y, I'm going to do 2 times this plus that, and then I solve for y there. So let's say, just for example's sake, let's say this was, I don't know, 30 degrees. So I'm going to do 2 times 30 plus y equals 180. So I get 60 plus y equals 180. So in other words, y is going to be about 120. So that's how we solve for these. You don't have to use any fancy like angle symbols or anything like that. I don't think, because Mr. Jose is the one that grades it, I don't think Mr. Jose is too picky on that. Just as long as you're showing your work and you show you're understanding it. Moving on to the next one. This is the part that gets a little tricky because it's like using Desmos, but it's not really using Desmos. I don't want you guys getting confused by their answers. So give me a second. I'm going to log into the student account one. So just to make it look a little more similar, we're going to do it on the student one. Also, this gives me the chance to let you guys know. If you guys ever get your assignment sent back, make sure you're reading the comments. Also, if there is no comments or anything, look here. Sometimes Mr. Jose uploads a PDF and he'll write it right here. You just click on it and you can see what you got wrong and what you need to fix. Let me go into vectors. It's kind of weird that you guys are studying vectors right now because this is more of a pre-calculus thing, but I guess they're getting you ready for it. It's just weird to me. So, whenever we're thinking about vectors, we want to think of it as our terminal point minus our initial point. What this does by doing our x2 minus x1 basically, comma y2 minus y1, the 2 being our terminal point. So the x value of our terminal point, y2 is the y value of our terminal point. What this does is it would give me a vector from the origin. And that's a little more useful because you can do this anywhere. Like, let's say I had another point here and I'm like, oh, I want to go vector v. I'm just going to add the x value that I got there. So I'm going to add the x value that I got. And then I'm also going to add the y value that I got. And it's going to create this vector right here. So it allows me to kind of move somewhere. Think of it as your movement. A vector is like your movement of something. Like I said, we just covered this in my pre-calculus class, so this is useful for when you're moving and stuff. So what I'm going to do here is how can you find the magnitude of the change? What it means by magnitude is how much are you moving? And if we think about that, if we're thinking about how much are we moving, that's basically the distance. So how I'm going to start it off, and you guys can use your own word for it. I'm going to say magnitude is basically the distance from the initial point to the terminal point. What I mean by this, and you can say it easier, it's basically the distance from where we start to where we end up. Way easier words. So don't just use my words because they sound fancy. Use it in your own words. It's basically the distance from where we start to where we stop. All right. So we can use the distance formula, which is basically the Pythagorean theorem, which is basically Pythagorean theorem. If you guys are ever stuck, like, what the heck is the distance formula? Just think of it as c squared equals a squared plus b squared. The reason why this works is, like, let's call this my a, and I'll just leave it green for b, and that's my b. Well, the distance of my a is my terminal point, that squared, and then I'm going to be adding these values and square it, and I want to find the distance. So I'm going to call this d, but I don't want d squared. So I'm going to square root the other side. That way I just have d. So that's how we do the distance formula. Nice and simple. So when I'm doing this, how can you find the magnitude? Where the horizontal change and the vertical change. So we're just doing that. I'm assuming they want you to solve for it. So when I'm doing this, this is already a change. This is a change of 3, and this is a change of 5. So this is pretty simple. So all we're going to do here is d equals square root of what are we doing here? Oh, 3 and 5. 3 squared plus 5 squared. So d equals square root of 9 plus 25. So in other words, d equals the square root of 34. And you guys can just leave it like that. And we're going to do the same thing for part B. So I'm not going to solve this because I want you guys to, like, solve some of it on your own. So d equals square root of 4 squared plus 7 squared. And you can use a calculator if you need it. There's actually a calculator tool right here. Or you can use Desmos if you want to solve it that way. But that's all you're doing for this one. So question 2, now we're going to be talking about an angle. So thinking about this, we have an opposite side. Our opposite side is basically our y value, and our hypotenuse, or our adjacent. Our adjacent is basically our x value. So similar, use trig to calculate the ratios. So again, we're going to use the same, what was it, 3 and 5? 3 and 5. So I'm going to write down a formula. I'm going to say that tangent tangent of theta equals my x, or I'm sorry, my y, because my opposite was y, over my x. So therefore, I could say that theta, because I'm solving for theta equals tangent inverse of y over x. Now I can plug my values in. So if I'm plugging my values in, I'm going to say that theta equals tangent inverse of, put my fraction, 5 over 3, because my vector was 3/5, or 3 comma 5, meaning my y was 5. And you guys can plug that in. What I recommend doing is going on Desmos. Going on Desmos and using their scientific calculator. And go to functions and type it in. So again, since it's a graded activity, that's why I'm not solving everything for you. You have to plug this in and give me your answer. All right, so suppose it's in quadrant 2, 3, or 4. How are we going to find the angle then? The angle between the vector and the positive x-axis will be greater than 90 degrees in this case. Okay, so if we think about it this way, it's saying like, what if we were in quadrant 2? So let's kind of review our quadrants real quick. 1, 2, 3, and 4. So if I look at this and I think of my vector being in quadrant 2, I'm like, wait a minute. That means that I'm going to have my x value over here and my y value over here. And I want to figure out, give me a second. I want to figure out this angle. But if I do it the way I did before, I'm only getting this angle. So that's weird. So this is kind of where knowing what lines do helps us out. So this, think about this as a straight line. If this is my theta, if the purple is my theta, when this is in quadrant 2, I want to do, so if it's in quadrant 2, I'm going to call it Q2. You guys should type it all out. Q2, it would equal, so our theta, I forget how they write it down. They write it down weird. I would say that let's say they usually call it alpha, but I'm going to say that alpha equals 180 minus theta. Technically, it's supposed to be the other way around. They always say like the angle you want is always your theta. The angle that you're solving for is your alpha. So I guess I'll do it that way. So my theta equals 180 minus my alpha. So that's if it's quadrant 2. So now we're going to do it for quadrant 3 and 4. So if I look at quadrant 3, I kind of have the same problem, just a little different. So here's my angle, or that's my x, that was my y. So now I have a negative x and a negative y to get to quadrant 3. So here's my new alpha. Well, now not only is it going to be this 180, so now we're including all of the 180. I'm not subtracting anymore. I'm also going to include this alpha. So another way of saying this is when your vector, so when, I'll type this part out for you guys, just so you guys see how you do it. So when the vector is The vector is in Q3. I should type it out. Quadrant 3. You might have to use this, unfortunately. Theta equals 180 plus alpha. So it looks similar, but it's a little different. I always draw my alphas a lot different than how the computer draws it. I don't know why. The computer makes it look like an A. So when it's in Q3, we're just gonna do 180 plus alpha. When it's in Q4, let's look at Q4. Give me a second. I'm just gonna erase everything. So when we're on Q4, our angle is gonna look like this. So here's our new alpha. Well, in this case, it's like we want all of this except for that little itty bitty side. Well, if I look at that, that kind of looks like a circle. So circle has 100 and has 360 degrees. So I want my entire circle, but I don't want this alpha. So the way I'm going to write that down is I'm just going to say when it's in quadrant 4, I'm going to do 360 minus that alpha. So instead of 180 minus alpha like I did in Q2, or adding alpha, in this case we're talking about 360. So let me request to do it. Okay, cool. We'll be able to get through it. So now try a numerical problem with the direction this. So we want to figure this out. All right, so what is this direction? So I'm going to start by making a drawing. So first I'm going to go -1, and then I'm going to go up 6. So thinking about that, I have to realize what quadrant I'm in. And I'm like, okay, I'm clearly in quadrant 2. So by doing that, I'm going to say that my adjacent is -1. Let me go back to purple. My adjacent is -1, and my opposite is 6. So in order to solve this, I'm going to say that tangent of, I'm going to call it alpha because it's in the wrong quadrant. Tangent of alpha equals 6 over -1. So in order to solve this, I'm going to say that alpha equals tangent inverse of -6. I just did 6 divided by -1. And then once I figure out what my alpha is, it's in quadrant 2, so I have to do 180 minus my alpha, so whatever I get for alpha, is equal to my theta. And that will give me my answer. All right. So that's how you do these. So you have to make up the rules here. Once you have the rules, it's going to help you in part C. All right. So are these vectors, and those vectors parallel? So if we want them to be parallel, we need to figure out what their angles are. So let's see what these angles are. So let's draw these out. So if I draw these out, I'm going to get, it's positive. So I have square root of 3 and 1. And if I do it the other way, this is negative square root of 3. So let me do a different color here. Negative square root of 3 and -1. So we need to figure out if these are parallel. So we need to figure out what their angles are. Okay, so to show your work and explain. So besides drawing it, two vectors are parallel if they point in the same direction or if they point in opposite directions. So I need to figure out if they're pointing in opposite directions. So they should be 180 from each other. So they're either going to be, in other words, it's going to be if theta 2 minus theta 1 equals 0, or if theta 2 minus theta 1 equals 180. Because if this is 180, then we're good to go. So we need to do a bit of work here. We need to figure out what our thetas are, and then figure out if they're 180 degrees apart or they're exactly the same angle. So if they're the same angle, if we subtract it, they should be equal to 0. All right, so first things first, I need to figure out my degree here. So if I figure out my degree, I'm going to do, again, this is in angle 3. So what I'm going to do here is I'm going to do, let me do the first one first. So I'm doing vector 1. So for vector 1, I'm going to say that tangent of theta, and I can do theta because I'm not going to subtract or anything. I'm just calling it theta right off the bat. Tangent of theta is equal to 1 over square root of 3. So in other words, theta equals tangent inverse of 1 over square root of 3. So you don't have to do anything fancy because you can literally just plug this all into Desmos. So do your tangent inverse, and you're going to do 1 divided by, 1 divided by square root of 3. And we get about 30 degrees. All right, so that's all you have to do for that one. So that's our theta 1. The other one is similar. We're going to do the same thing, except now they're both negative. So it's still positive. So negative divided by a negative, and it's like, oh, well, if we do that, that's still positive. So it's the same angle. So make sure you're showing your work. You're showing that they both equal 0. So this one we would say they are parallel because they result in the same angle. Or they're not technically the same angle because remember, we still have to do 180 minus, not minus, plus alpha. So they're 210. So after we do this, we're going to say 210 minus 30, and we get 180. So they are parallel. So they are parallel. And we're going to say because they are facing opposite directions. Because they face opposite directions. So you just have to type all of that in. All right, so are these vectors parallel? Show your work and explain. All right, so again, I don't think I really have to draw the picture here. So I'm going to say tangent theta equals 3 over 2, which means tangent inverse, that's supposed to be an inverse sign, the -1 symbol, 3 over 2. So theta equals this. That one's easy because it's obviously in quadrant 1. This one's in quadrant 3. So that one's a little different. So I'm going to say tangent alpha, because again, we're going to have to do math to figure out the actual theta. Tangent alpha equals -2 over -3, which means alpha equals tangent inverse of 2/3. And then after we figure that out, we still need to figure out our whatchamacallit. We still need to figure out our theta. So theta equals 180 plus whatever we get for alpha. At this point, we need to make sure that whatever theta 2 is minus theta 1, it has to equal 0, or in this case, it has to equal 180. Because we know they have to be either opposite sides or negative sides. And that's pretty much it, guys. That's how we do this activity. I know it's like a lot of symbols, but now in case you've ever seen those weird symbols on like math chalkboard, you kind of get an idea of when they're using alpha and when they use theta.